welcome to all of you in this lecture. Today I will be speaking on very different topic of applied mathematics, which is not taught in many courses, but it has enormous applications if you are working in the field of applied mathematics. So what is this topic? Is wavelet analysis. This is a very important topic in the area of applied mathematics, as I have already said. But before going to say something about the wavelet, let me give you the mathematical foundation behind it. So for that reason I am starting with the very basic spaces, which we call it as a vector spaces. As all of you are familiar with the vector spaces, because vector spaces play an important role in many branches of mathematics, and it has some operations on it. So vector space, the element of a vector spaces does not mean vectors which we see in the coordinate geometry. Element of a vector spaces can be a functions as well, vectors as well, anything sequences as well, as we all know already about it. So one of the vector spaces example, let me give you LP space for p is greater than 1. So the element of this vector spaces can be written like this, which is basically a sequence which satisfy this property. So LP is an example of a vector spaces which where the elements of a vector spaces are sequence. Okay. So is it clear to everyone that vector, what is vector spaces? I am not giving the basic definition of a vector spaces, and I assume that all of you know this. Okay. If you now, after vector spaces, what is the main mathematical object defined on the vector spaces is, which we call it as a basis. A basis B of vector space X over a field K is linearly independent sets, subset of X that generates X. We all know what is basis. A basis B of a vector space X over a field K is a linearly independent subset of X that generate X. So I am not going to explain you what is linearly independent subset, and I am assuming that all of you know what are linearly independent subsets. So now, if basis contains finite number of elements, it is called finite dimensional spaces. If basis contains infinite elements, it is called infinite dimensional spaces. So if, let me ask two questions: what will be the dimension of a space, vector space R2? So the answer should be 2. What will be the dimension of the vector spaces LP? P is greater than 1, which I have defined just now. The dimension of this vector space will be infinite. So this is called infinite dimensional vector spaces, this is called finite dimensional vector spaces. So it should be clear to you that what is the difference between finite dimensional spaces and infinite dimensional spaces. Okay. So now I am coming to the concept of a normed spaces. So what are normed spaces? A normed space is a vector space with norm. What is the concept of a norm? Norm is which we define to measure the size of a element of a vector space. So basically normed space is a vector space with norm defined on it. More mathematically, the norm space is a function, the function norm is a function from vector space X to R which satisfy the following axioms. And norm of X is 0 if and only X is 0. Okay. So, norm satisfy these three definitions. First definition is norm of X should be greater than 0 and norm of X is equal to 0 if and only if that element itself is a 0. Second definition is also if alpha is a element any real number, and the third property of a norm is called triangle inequality. Triangle inequality. Okay. So, now the norm on a vector space LP, which we have already discussed this vector space. So, what will be the norm on this vector space? I am giving you the definitions. This way we can define the norm. Okay. Clear to everyone? As I said that vector is the element of a vector space can be a sequence, element of a vector space can be a vectors, element of a vector space can be functions as well. So, this is the example of a different vector space, the element of which will be functions, okay, LPR. This is a very famous space which is a set of all measurable functions such that this property is satisfied. Okay. This is called LPR spaces, this is a vector space, and if I want to make it normed spaces, I have to define a norm on it. So, the norm on this vector space is defined by this. Okay, so we have seen two examples of a vector spaces. In this case, the element of a vector space was a sequence. In this case, element of a vector space was a function. Okay, and like simple vector spaces, we all know, we have already studied in coordinate geometry like R2, R3, R4. They are called finite dimensional vector spaces. So, now let me give you the explanation of a inner product space. Inner product space. First of all, I wanted to ask you a simple question, what is the need of inner product space? Okay, that I will, you could think when I am defining the definition of inner product, otherwise I will answer at the end. So, an inner product space X is a vector space. So, you know, normed space, inner product space, every space we are defining on the vector space. Okay. So, inner product space is a vector space with the inner product defined on it, like in normed spaces we were defining a norm on it. So, inner product is a function, it is a function from x multiplications by x. So, this is a multiplication sign and this is x is a vector space, x is a vector space to the field K, where this vector space x is defined. So, this field can be a R or it can be a complex numbers. So, this can be R or C. So, C is a set of a complex number, R is a set of a real numbers. So, if you want to make a differentiation between the inner product function and norm function, so it is a binary functions because it takes two operands on it, and inner product function satisfy following properties which I am defining now. 0 and x will be, this will be equal to 0 if and only if that element itself is 0. The second property is alpha x into y should be. Third property is x okay, and the last property is okay. So, if any any function satisfy these four properties, it is called inner product space. So, this inner product, an inner product space on X defines a norm on X by this. So, if this is the case, I can say all inner product spaces are normed spaces, but converse is not true. Not all normed spaces are inner product spaces. So, inner product space it will always be normed space, but not all normed spaces are inner product space. Okay, clear? So, now the question comes, when normed space can become a inner product space. So, for that reason I am defining, if norm introduced by inner product space satisfy the parallelogram law, means what parallelogram law says? So, if any norm satisfy this parallelogram law, then it will be generated by inner product, otherwise not. So, a norm which does not satisfy this property will not be generated by inner product. Okay, clear? Now, moreover, one another important property which will be used later on is called Cauchy-Suraj inequality. Cauchy-Suraj inequality. So, if x and y are two elements of a vector space, then this property will be satisfied. I am stating this property without proof, and this is a very famous property which is called Cauchy-Suraj inequality. If x and y are two elements of a vector spaces. Okay. Now, as I am answering my postponed question which I asked you earlier, that why we need inner product space. So, this is the time I can answer that question to you, and some of you might have already thought about it. Two vectors, if I need a concept of orthogonality, I have to introduce the concept of inner product. So, for that reason, two vectors x and y are said to be orthogonal if x this inner product is 0. So, to define the concept of orthogonality, we need the concept of inner product. Clear? Now, let me give you one example. The space LP, P is not an inner product space, not an inner product space. So, how can we prove this example? The space LP P is equal to not equal to 2 is not a inner product space. So, of course, it is a normed space. We have already defined the norm on it. So, if x belongs to LP, norm will be defined this way. Okay. So, we have to prove that for P not equal to 2, it is not an inner product space. So, of course, if I can prove that this norm does not satisfy the parallelogram, I can say it will not be generated through inner product. So, then my job is done. So, what will be, for that reason I am taking one particular x which is this sequence, another sequence I am taking 1 minus 1. Okay. So, what will be x plus y? X plus y will be, what will be x minus y? Clear? So, what will be this norm? This norm will be 2. You can compute it with the formula which I have given you. Similarly, this will also be 2, but what will be norm of x p? This will be 2 to the power 1 by p. Norm of y will also be p. So, if you look at parallelogram law, which is this, you will be able to see that for this particular example of x and y, this parallelogram law is satisfied only in case of a p is equal to 2. So, that is why it is an inner product space if p is 2, and if p is not equal to 2, it is not an inner product space. So, is it clear to everyone? So, this was the basic about vector space, normed space and inner product space. Now, I am going to define another important spaces which is called Hilbert space. Okay. So, in a very simple language, I can say a complete inner product space is called a Hilbert space. A complete inner product space is called Hilbert space. Okay. So, given a basis Vk, where k belongs to Ic. So, what this Vk can be a sequence, this can be a sequence of a vector, sequence of a functions. Okay. So, in case of a functions, we could write Vk x, k belongs to I. So, suppose we are considering f is any function which belongs to x, okay, h. For Hilbert space we are writing h, okay. So, if Vkx is a basis for h, we can write function which belongs to the Hilbert space like that. If we want to associate this coefficient with f, that is why I am using this notation Ck multiply by x, okay. So, if f is a vector, we could write this way, okay. That is just a notations, okay. So, why I introduced the concept of Hilbert space, as in a definition wise I said a complete inner product space is called Hilbert space, and most of the time you will see later on where wavelet is developed in L2R spaces, and L2R spaces is a Hilbert space, okay. So, bases are this. Now, I will introduce you 3 different concepts of a basis. Basis all of you already know, because all of you already know this linear algebra stuff. But now at the advanced level, basis also categorized into a different category, and what are those bases I am going to explain you. One of the thing I am frames, Riesz basis, and then I will come to orthogonal basis. Okay. So, I will give you definitions step by step. First of all, let me introduce what are called frames. Okay, what are called frames. Let me connect this frames definition with the previous thing. So, if I wanted to say that this Vkx are frames for a Hilbert space H, what are the conditions I need? That then I will be needing that if f can be written like that. Okay. Moreover, this Vkx satisfies some additional property. What is that additional property? I am writing that additional property here. Okay, for all f belongs to H. What is this small m and capital M? Small m and capital M are constants which satisfy this inequality. Moreover, when Vk satisfy this condition is called frames inequality. Okay, frames inequality, and small m and capital M are called frames bounds. Okay, if M will be equal to capital M, it will be a tight frame. Okay, and if M is equal to capital M is equal to 1, what it will turns out to be, I will come to that point later. So, all of you are clear with this frames definitions. Frames are basically Vkx which satisfy this frames inequality will be called frames. Now, this Vkx can be linearly dependent vectors in frames, but to come to the definition of a Riesz basis, one additional assumption which I am making, that this is a linearly Li linearly independent vectors. Okay. Of course, again let me make one more point. This vector does not mean that really these are vectors. Vectors means these are a element of a vector space which can be a functions as well. So, what is the difference between frames and Riesz basis? Riesz basis also satisfy the frames inequality. The only difference this time is that Vkx will be a linearly independent vectors, while in frames Vkx can be a linearly dependent vectors. Okay. So, now the third concept is orthonormal basis. In orthonormal basis, as I said, when M is equal to this is moreover Vkx is again a linearly independent vectors, then we call it as a orthonormal basis. Okay. So, now I will explain these three things initially according to the their properties, and then I will give you some examples. Okay. So, let me give you a one example. So, every orthonormal basis is a frames with M is equal to capital M is equal to 1, which is a frame bound. Okay. And of course, it is also a tight frame, because this small m is equal to capital M, then we call it as a tight frame. Okay. So, in each case we can write this way, but in case of a frames this will be a this can be a linearly dependent vectors. However, in case of a Riesz basis and orthonormal basis, this will be a linearly independent vectors. Moreover, frames will turns out to be orthonormal basis if this condition is satisfied. So, this should be clear to everyone. Now, why we need frames, why we need Riesz basis, why we need orthonormal basis? Okay? Because so far we used to study orthonormal basis, as some of you might have noticed in case of a Fourier series. E to the power I k x gives you an orthonormal basis for the corresponding space. But sometime we should notice that orthonormal bases are difficult to achieve. That is why we are relaxing those criteria to the Riesz basis and frames. Okay. So, but there is some advantage of frames also that I will tell you later on with respect to signal representation. Now, let me work out with one example given Vk x. Here I am working out with the index set n, which is a set of natural numbers, is an orthonormal basis for H. Then prove that does not form Riesz basis for H. Okay. So, first of all I have to, if Vk, it is given that Vkx is an orthonormal basis, so it will be linearly independent vectors, therefore, this will also be a linearly independent vectors. Now, I have to look at the frames inequality. Frames inequality, or sometimes it is also called frames conditions, whether frames conditions are satisfied or not, that I am going to check. What okay. So, now Vk is an orthonormal basis, so it will satisfy this thing. Of course, here you could consider both as a 1. But in this case, if you plug this inequality here, can you achieve a small m here? So, the answer is of course no, there does not exist m for which this inequality will be satisfied. In case Vkx, I will replace Vk by k. So, that is why we cannot, because it does not satisfy the frame conditions, that is why it does not form a Riesz basis. Clear to everyone? Now, another example let me take, given Vkx k belongs to n is orthonormal basis for H, prove that V1x, V1x, V2x, V2x, V3x, V3x is frame but does not form Riesz basis for H. Okay, so this is the example we are working. Given Vkx is an orthonormal basis for H, prove that this set where we have repeated each entry V1x, V2x, V3x is a frame but does not form a Riesz basis for H. Why it will be a frame? If Vkx is an orthonormal basis, it is also a frame with frame bound 1, but so it will become frame bound frames with frame bound 2. You could prove easily that if this set satisfy these conditions, so basically norm of f square is okay. Then in this case what this frame bound will be 2 okay. So, but this it is a linearly dependent set, not Li set, therefore, it does not form a Riesz basis for a Hilbert space H, clear. That is the example. Now, if I give you another example where I cut this term, now you have to tell me whether it is a frame or not. It will be a frame. Next question is, will it form a Riesz basis? No, it will not form a Riesz basis because again it is a linearly dependent, some of the vectors are linearly dependent like V1x is repeated, V2x is repeated. But what will be the frame bounds? Frame bounds might be different. Okay. So, given Vkx is an orthonormal basis for H, prove that is a frame but does not form a Riesz basis for H. Okay. So, now another example I can take, if there is a frame Vkx, not example, another property of a frames, let me mention in another page. If Vkx k belongs to I index set, or you can also consider that as a natural numbers, is accompanied by dual frame. So, if this is a frame, then there exists a dual frame Vkx tilde k belongs to I. So, whenever there will be a frame, there will be a dual frame. It will always be accompanied by. So, in this case, I can write this, or this can also be written like okay, for all f belongs to H. If frames are, so again if frames are linearly independent set for H, then frames gives basically a Riesz basis. Okay. So, now in case of a Riesz basis also, dual frame will also be a Riesz basis and biorthogonal. Dual frame, if frames are Riesz basis, dual frame will also be Riesz basis and biorthogonal. Okay. And what is this property biorthogonality? Biorthogonality property or dual frame will always satisfy this property. Okay. Dual frame will always satisfy this property. In case of a Riesz basis, this dual frame will also be Riesz basis and biorthogonal. Because of this property, we are able to write this if you look at it. So, now the question comes up, what is the advantage of frames? Okay. Because if you feel the difference in the definition, frames are allows us to write the expansion of a function f in terms of a linearly dependent vectors. So, it helps in representing the noise of a signal. Okay. So, in a nutshell, frames are like increases flexibility in representing the noise of a functions, or basically whereas the basis. So, in a nutshell, or maybe I can write on new page, bases are optimal for fast data processing, whereas redundancy inherent in frames increases flexibility when used in expressing signals or approximating a function. It also adds robustness to the noise in the data, but at what cost? It is means, as I have already said, bases are optimal for fast data processing, whereas redundancy inherent in frames. This redundancy means in terms of a LD vectors you could measure, whereas redundancy inherent in frames increases flexibility when used in expressing signal or approximating a function. So, this linearly dependent vectors are also helping in some way to us. Okay. It adds robustness to the noise of the data. This redundancy adds robustness to the noise in data, but at what cost? That is a main concern for us, at the high computation cost. So, the answer to that concern is at the price of high computational cost. It adds robustness to the noise in the data, but at the price of high computation cost. Okay. So, this anyway, this later on I will take one example where I will explain you how bases are helping in fast data processing and how frames are helping in representing robustness to the noise in data at the cost of high computation. Okay. So, the difference between frames, Riesz basis and orthonormal basis should be clear to you. This is the main motivations behind this lecture, because later on to wavelets I need these concepts. Okay. Because many people are like very furious, or like they do not understand what is basically wavelet. Wavelets are simple one of the basis functions. Okay. Basis functions. Sometimes wavelets are frames, sometimes wavelets are orthonormal, sometimes wavelets are Riesz basis. So, that is why it becomes very important for me that you understand these three things: frames, Riesz basis and orthonormal basis. Okay. So, wavelets are simple basis function, nothing else. And if you look at the application of a wavelet in applied mathematics, they are enormous. Okay, enormous I should say. But to understand it more clearly, First of all, you should have a grasp on three different things: frames, Riesz basis and orthonormal basis, and that was the motivation behind this particular lectures. In the next lecture, I will take some more examples to explain you how bases are helping for fast data processing and how frames are helping in representing signals, of course at the price of high computation cost. That I will consider in my next class. So, thank you for today's lecture.